Hello everyone, my name is Matt. Welcome to this presentation. Today we're going to be talking about semi-rigid connections and how to model them in SRAM. So today we're going to take a look at some of the use of semi-rigid connections in structural modeling, analysis, and design, with a focus on the info that you're going to need to get up and running today. We're going to discuss some of the best practices and tips for working with these types of connections and go through a couple examples as well. And hopefully by the end of the webinar, you'll be more comfortable with semi-rigid connections and as well implementing them in SRAM. I'm going to start off with an introduction. My name is Matt. I'm an application engineer at SRAM Software in Vancouver, British Columbia. And I'll be leading the presentation today, but I'm also joined by a few of my colleagues who will help answer questions on it. One of my colleagues is actually responsible for the development of a white paper on this very topic, and a lot of the implementation of this capability within SRAM. That's Dr. Siriwit Sasabut, and he's actually going to be the one, he's the one that provided a lot more of the technical content for this webinar, and also, again, as I mentioned already, wrote a white paper article about this topic as well. And in this presentation here, we're going to look at a bit of a background to semi-rigid connections first. Then we'll look at how it's implemented within SRAM. We have a case study to go through just to help you understand the topic a little bit more. And we have a few other additional resources that might be of interest to you. Once we're done with all that, we'll wrap things up with a summary. We'll also open the floor then for questions, and we'll have a few more announcements at the end of the presentation as well. This is also a good time to go over SRAM Software, the company, and our products. So let's just start with SRAM. At the center of our product offering, we have SRAM, and it's used as a 3D FEA modeling, analysis, and result post-processing tool, but it also has some design functionality. And we'll be looking at SRAM throughout the presentation today. Steel design of complete structures can be performed with S-Steel, which is fully integrated within SRAM, or with SPAD, which is a standalone product. And on the topic of steel design, if you're using the Canadian Steel Design Code for steel design, SRAM Software has actually produced a document, a steel design document with a number of examples following the American Institute of Steel Construction guide using the Canadian Steel Code. And that's available. Just contact us if you'd like more information about this. It's free to download, and we've also solved them not only by hand, but using SRAM and S-Steel as well, so you can compare the results. Now back on track here. For concrete beam, column, and wall section design, it's handled with S-Concrete as either standalone or integrated within SRAM. That's using the Integrated Concrete Design, or ICD. And S-Line is a continuous beam design program which can be operated as a standalone as well, or also integrated with SRAM via the ICD. And the 5 products that you saw on the left-hand side of the screen there, those make up our classic line of products. And on the right side, starting with S-Calc, we have our new generation products. S-Calc, the first one you see here, is a general section properties calculator. So it includes different types of sections, and you can build your own sections, combine sections. And it calculates results like shear areas, warping constants, and so on that can be used within your analysis model. S-Foundation, which its name probably implies, is used to analyze and design all types of foundations, including those supported by piles. And lastly, the most recent addition to our product suite is S-Timber for the analysis and design of timber structures. And these new generation products have a modern look and feel, and they feature capabilities that allow our users to automate repetitive tasks, customize how the products work to better fit their workflows, and they also allow for easy deployment of these automations and customizations throughout an engineering organization using wizards. In addition to the integration among our own products, engineers can also import and export from AutoCAD through DXF files, BIM programs like Revit and Tekla, Microsoft Office Excel sheets, Access databases, and export reports to Word. And we've also added the capability to export from 2 other engineering programs, namely ETABS and STAT, to enable engineers to perform further analysis and design within our products without having to rebuild models already built in these third-party products. So let's start with a bit of background into what semi-rigid connections represent. So we'll look at a background as well as some goals and advantages, some typical joint behavior, if such a thing exists. Also, how do we actually define something as being rigid, or a connection as being rigid versus non-rigid? How do we classify these? So we have a few different topics to get through. Now, historically, engineers would often simplify their joints as being either fixed or pinned. And that's oftentimes done with structural analysis models. Oftentimes, you guys have a lot of other work to do. You may not have all the necessary information, and this is oftentimes a reasonable simplification. Now, as the software development has become more and more robust, these products have allowed you to do the same, but they're now actually allowing you to do more and more with your connection model. So now this assumption that joints are either pinned or fixed is no longer always accurate, and a joint may always fall, or may also fall somewhere in between. Now, why might we want to model semi-rigid connections? Well, they can actually allow us to model more accurately. The reality is that joints are never fully fixed or fully pinned, and engineers are often required to make assumptions for simplicity's sake. But accurate modeling provides clear advantages, as we'll see. And being able to design more efficiently allows us the ability to optimize our structure's true behavior and reduce material and construction costs. We also get improved accuracy, so we get more accurate global deflections and forces, and we'll see more examples of this as we go along the webinar. It's also a nice way to test our assumptions. Rather than assuming a joint's moments are negligible, why not make the connection with realistic stiffnesses and find out? And I'm sure if you've been using SRAM or any other analysis software in the past, you've come up with some unstable model at some point. And semi-rigid connections are also, they also provide you a way to remove instabilities that may only exist due to model simplification. Perhaps you've oversimplified your joint connections to the point where they don't withstand any moments, when in reality they would, so you're not truly representing your model in the most accurate way. This gives you another option to try out when modeling. Let's first look at a few different connection options first. So if we have this simple frame here, and we know we have pin connections between the beam and the column, that means that we have a large moment at the midspan, and we don't have any moment in our columns. Again, the connection between the beams and the columns isn't transferring any moment. Now, if we instead had a fixed or rigid connection at the beam-column interface, what this allows us to do is allows us to reduce the beam moment, but it also does induce some moments elsewhere. So you can see that we get some negative moments where the beam and the column meet, and we also get some moments in our column. And one of the drawbacks of this is that it can increase the construction costs. So this is using fully fixed connections, or fully rigid. Now, somewhere in between, you might find a happy medium. And engineers will often employ semi-rigid connections to their structures to find somewhere in between. Now, in the spectrum of connection types, semi-rigid connections offer more simplicity than rigid or fixed connections, while also reducing the moment demands, especially in the beams like we saw in that last example, when compared with fully pinned connections. Now, obviously, this will vary sometimes depending on geometry and the applications, so we are kind of speaking in general terms here. Now, perhaps to put this into perspective here, we can plot the connection rotation versus connection moment for common connection types. So if we have a fully pinned connection, we'd have a large rotation with very little moment. And if we had a fully rigid connection, we'd have a low rotation with a very high moment. And in between, we have all these other semi-rigid connections. So how do we know what to consider rigid versus pinned connection? So to quantify my connection stiffness versus member stiffness, this is one way that we can do that. We specify the connection stiffness relative to that member stiffness. Now, hopefully we already know the member stiffness. We're kind of going in with the assumption that we know which type of member we're using, which section, and so on, and which material. So we have an idea of the stiffness of the member already. So we have to determine the connection stiffness, and it's not always an easy task. And this can be done through real-life experimentation. It's also possible through finite element analysis, and SRAM actually has the ability to model connections and members also with shell elements. You can convert your members into shell elements and connection locations to study the connections and their stiffnesses. Now, for the practicing engineers, or most engineers, I should say, they'll use a standard connection type, and their stiffness can be found in connection tables. Now, there are a few different definitions of connection stiffness, and I've just highlighted a few of them here. This is by no means a comprehensive list. But they classify connections based on their stiffness relative to the member, like I mentioned before. Now, a couple examples we can pull from here. In the Eurocode example, if a connection is 25 times stiffer than the member, it's considered rigid. Now, one thing to keep in mind here when we're comparing the Eurocode and the American codes is that the Eurocode uses the initial stiffness, this one here, Ri, whereas the American code uses secant stiffness. So just keep that in mind if you're comparing the two. The Eurocode also has different criteria depending on if the frame is braced or not, as you can see. So in summary, we hope that through this brief explanation here, you now have the idea that you can use rigid or semi-rigid connections to model your structure more accurately, and also hopefully design more efficiently once you get more realistic loadings within the correct elements in your model. So now let's take a look at how we can implement semi-rigid connections into our SRAM models. Essentially in SRAM, there's two different ways to do this. We have the partial release tool and the elastic plastic link beam. Partial release tool is the one we're going to be focusing on in today's presentation. It's definitely quick to use. It's also faster for the analysis. Your results are much easier to digest. The behavior is all linear, and again, you specify the stiffness relative to the member stiffness. The elastic plastic link beam is definitely powerful. It's a more general approach, but it does require a bit more in terms of setting it up, and also requires a nonlinear analysis to truly understand nonlinear behavior. So for that reason, we're going to be focusing on the partial release tool for this example, or for this webinar. And just for your understanding, as we go through some examples, this might become a bit more clear. SRAM uses a user-defined percent release. And what this means is that if it's 100% release, or pinned, sorry, we'd enter 100% release. If it's 0% release, that equals a rigid connection. And if we have a 25% release, that means that the connection has 25% less stiffness than the member. So think of this as a percent, or think of this percent as the percent the connection is less stiff compared to the member. Now we can also calculate this from the end fixity factor, if we know the percent release. So the value, Rj, is the stiffness of the connection. And this gives us a way to calculate our percent release by knowing our connection stiffness. And there's actually a resource that we'll refer to at the end of the presentation that gives you more information on this. But using SRAM's member end release tool, the one that you may already be familiar with, we can specify whether we want a fully pinned release or a partial release from the data bar. And we can even enter the percent release there. So we're going to go into an example now. I have this simple model open right now. And if I look at the release tool, I can see that I don't actually have any releases on my members. So these members connections are all moment connections at the moment. And I can go to the loads window, and I can see that I have just one load case. And if I just display my loads, you can see that it's comprised of 0.5 kilonewton per meter UDL, and then I also have a 2 kilonewton joint load in the X direction. So I'm going to analyze this based on the existing components or parameters that we've defined. So go to Analyze and just run a linear static analysis. And here within this linear static analysis, I'm just going to look at some of the details. I can look at the deflections if I'd like to, but what I'm most interested in right now is actually the moment diagrams. So click on moment diagrams and looking at the Y moments. And I just want to get a feel for what these moments are. So I can see in this column here, for example, if I right-click, I can go to Properties, and I can see that the moments seem to max out around 2.49 kilonewton meters. That seems to be where the maximum moments appear. And in the beam, I'm getting a maximum of about 1.52 kilonewton meters from a maximum positive moment, and again 2.49 in the column. Now let's go back to the geometry, and we're going to make a small change. We're going to say that we only define this as a moment connection because we didn't have a way of defining it any other way other than pinned. We could either choose from pinned or moment connections. But now we do have the ability in SRAM to choose between fully released, moment connections, or a percent release. And what I could do now is I could add a 50% release in both MY and MZ and apply it to this beam here. And I can choose to view the percent release if I'd like. We can see there. And I can reanalyze. And everything's just happening on my other screen here, so I get a reanalysis. And now when I look at my moment results, I can see here that my positive moment has surely gone down. If I look at my moment, my beams, you can see that this has gone down slightly, 1.72. As also my negative moments at the connection between the column and the beam have gone down, which is definitely good if I'm trying to design this. I get more of a, I guess, an amenable result for this type of design, something that's a little bit easier to work with. Now we're going to look through some more examples here, but I'm just going to go back to the slides for a little bit. Something we talked about earlier was how we can use semi-rigid connections in troubleshooting of our models. And it's a great tool for that type of troubleshooting, especially if our model might be unstable. It can actually help us confirm whether there's an actual stability issue with our real design rather than just our assumed design where we're assuming something's either completely pinned or completely rigid. And it also helps us determine whether or not the instability exists due to oversimplifying the model. And again, that kind of goes back to the first point. And perhaps to explain this a little bit clearer, I can open up another model that I have. So I'm just going to go back to SRAM. And here's my model. As you see, I have my release tool selected. So you've already seen my releases. I have all my horizontal members released. And you can see they have both MY and MZ releases. We don't use MX releases. MX basically means that we're releasing a member about its own axis, allowing it to rotate about itself. And that's not commonly used in structural engineering, but if you did have an application for it, by all means use that with the member release tool, full release. So if we look at some of the geometry here, we can see that we have pin supports and we have released beams. And if I look at my loads, I'm just considering self-weight at this time. So what I want to do now is I want to go ahead and run an analysis. And for this example, I'm going to run a p-delta static analysis. Press OK to run this. And when I move over my solution trail here, you can see that we're actually getting some diagnostic messages that occur during the analysis. This is again during a p-delta analysis. I'm getting this k-negative definite diagnostic message. And I can always look this up here at the document that's referred to in the screen text. But I happen to know, just through experience, that this k-negative definite is indicative of some sort of instabilities in my model. And it's giving me nodes and degrees of freedom where I might have instabilities. I'm just going to press enter here. And the thing to understand here is that we are getting some results. But even though we don't have any loading except for the self-weight, the model is unstable. And this is something that we commonly come across within our technical support team in terms of why a structure might be unstable. Well, they usually, oftentimes it will revolve around some release conditions. And again, we work in a mathematical environment where a pin support is 100% pinned and a release connection transfers absolutely no moment. However, SRAM doesn't have that limitation. Let's just say that we want to try something in between. We can just select our horizontal members, the only ones that are released. And I'm going to remove these releases. And instead, I'm just going to use a percent release. I'm going to say that they're 80% release. And I'll just press OK here and apply this to all of my members here. And I can verify that 80 has been added by pressing View percent release. And that's good there. So I've updated my model. My horizontal members have been released partially. And now I can rerun my analysis. I rerun this p-delta static analysis. And if I drag my solution trail over, you can see that we're getting a clean solution this time, which is exactly what we want. And if nothing else, even if we didn't want our connections between our beams and columns to be partially released, and we didn't want moment in our columns, this tool still allows me to quickly isolate where this instability might have occurred. And it was pretty clear to me there that the instability had something to do with my moment releases, and something might need to be done. And now I can look at my moment diagrams here, and I can see that I am getting a bit of moment within my columns, which I wouldn't have had if they were fully pinned beams. So hopefully through this, you're able to understand that it's quite simple to define a partial release within SRAM. You can still use that same moment release tool. And we like to think that there's no additional modeling difficulty once you've determined the stiffness of your partial release. And the beauty is that it doesn't increase the analysis time either. It's easy and it's very quick to analyze. And we can take a look at this through another quick example as well. Now this example, we're going to have a series of frames, like you can see here. So we're going to have a 2-bay 11-story frame. It's going to be made of steel. And we'll look at how the results vary with varying degrees of semi-rigid connections. So we're going to observe the results as they vary. And we'll compare our results to hand calculations and a third-party software. Now the hand calculations, for your reference, are in that white paper that I'll refer to at the end. It's available from our website and also from our online help resources. So let me just go back into SRAM here. And I'm going to open up that model that I was referring to. And you can see here, if I just change my view to make it a little bit easier to digest, we have 5 different frames representing the same geometry, with the only difference being the percent release on each of the connections between the beams and columns. So if I look at my release tool here, you can see, maybe I'll just rotate so it's a little bit easier to see. On this side, we have fully rigid connections. There's no releases. If I view my percent release, you can see that now I have 25% release on this, these beams here, 50 on this one, 75 on this one, and 100% on this one. And I can also look at some of the properties, so I can look at the section properties and see that we're using similar sections for each one of these. My supports, I have fully fixed base supports. And for my loads, you can see that I have one load case with all my loading, and I have some UDLs, and I also have some lateral loads. So the structure is exposed to both. So at this stage now, what I'm going to do is I'm going to analyze, and I've actually filtered this into different groups as well. It's a little bit easier for me to compare side by side. Now I'm going to analyze this model, just running a linear static analysis. And we get a clean solution with no diagnostic messages. And what I'm interested in most right now that I'm in the graphical results window, is looking at the deflections. So I'm going to look at the deflection tool here, and you can see that SRAM scales the deflection relative to whatever is deflecting the most. So we can see here on the right-hand side where we have a fully pinned beam, we're getting a lot of lateral deflection. And if we look at the X deflection values, you can see they vary between about 130 millimeters on this left-hand side model to almost 7,000 millimeters on the right-hand side model. So you can see why we might get some instability issues if we're running fully pinned connections in all of our models, in all of our beams. Now I can also look at some of my deflection, or some moment diagrams, and maybe I'll just turn off the display of my numerical values. It's a little bit easier to see. And just comparing them side by side, we can see here that our columns are getting a lot more moment in this fully pinned example, which may or may not be what we wanted. However, in this one, with this fully moment connection model, we have much more even distribution of moments throughout our structure. And we're kind of gradually increasing to more moments at the base as we become more and more of a pin connection in our beams. And the same thing would also occur, we're looking at our results for our reactions. Now really what I'm getting at here is we can see the influence, in this case here we're just looking at roof deflections, and we compare results between the first and second order analysis. In this case here we just ran a linear static analysis in our example, so that's the first order analysis. But in SRAM we can also run second order analysis, being P delta or nonlinear analysis. And we compared this to hand calculations and also third-party software. And we can notice consistently higher deflections at roof level as the percent releases increase. So we can see as we're approaching the fully pinned connection for our beams, we're getting higher and higher lateral roof deflections. And that doesn't matter which source we're using, it's pretty much consistent that we're getting higher deflections. And just for your information as well, the maximum difference between the theoretical hand calculations that were used and SRAM's results was about less than 0.75%. So we were quite close to the theory example that was used. And you can also find that through our website, sframe.com, under Downloads, How to Model Partial Releases. You can find the references that we're using. Now, just one last topic we're going to talk about today is some further topics on this semi-rigid connections that we've been talking about. So we could also consider the nonlinear material properties that are connections using nonlinear semi-rigid connections and link elements. There's a couple other considerations we can talk about as well. And I have a few suggested references you may want to check out if you work with these semi-rigid connections often. Now for the nonlinear semi-rigid connections, SRAM has a link element tool that has several hysteretic material models that you can use. So there's also user-defined loading and unloading curves. This does require nonlinear analysis, so the complexity of the analysis does increase, but you are getting more robust results. And the difference here is that the stiffness of your link element is defined based on the member end link element properties, and is not dependent on the connecting member. And if you're curious about this, you can find more details in our help system. You can also go to member type tool in SRAM, and then it's under the elastic plastic link beam. A few other ways that you can consider this type of behavior. You may want to further describe this type of behavior with your steel design model using effective lengths. And you could also use strength-based semi-rigid connections. And this list of suggested references is available in the document that I was referring to. I'll just bring it up before we open up the floor for questions. But again, this is available from our website, so I encourage you to check that document out. I'll show you where to find that in just a second. So again, what you can do, you can go to Help, Online Resources, and under SRAM Analysis Documents, you can see that there's a partial releases case study. And if we open this guy up, you'll be able to find more information about the topic we covered in today's presentation, and a lot of the formulas and the example model as well. So it brings an end to the demo portion of this presentation. We discussed a bit of a background of semi-rigid connections, as well as how they're implemented in SRAM, and we even went through a case study showing that in a little bit more detail. And hopefully, for those of you that are interested in taking this a step further and going with nonlinear material modeling for your joint connections, the ability to use link elements is another way you could take this even further. So I just have a few summarizing points before I open up the floor for questions. So with this, I hope you took away from the fact that in SRAM you can use partial releases to model your structure more accurately, assuming that you don't have completely pinned or completely rigid connections between your members. It allows you to design your structures more efficiently as well. And there are two different ways that you can approach this. We really just focused on number one. If you're interested in the second approach, you're more than welcome to get in touch and we'll provide some more details.